Welcome to the Deep Dive. Today we're diving into some fascinating physics concepts with excerpts from the Feynman lectures on physics.
Feynman lectures are always a great place to start.
Right. We're going to unlock some aha moments about how objects balance and rotate. You might be surprised by what you discover. So let's jump right in with center of mass, or CM. It sounds kind of technical, but what are we really talking about when we say center of mass?
It's simpler than it sounds. Imagine any object, a basketball, a car, even something as complex as a spaceship. Each of these objects has a single point where all its mass seems to be concentrated. That's its CM.
So it's like a balancing point for the whole object.
Exactly. Think about a seesaw. The CM is where you'd put the fulcrum to balance it perfectly. Feynman uses a cool example, a hoop. Its CM is actually in the middle of the empty space, not on the hoop itself.
That's pretty wild. It's like the object's gravitational center, right?
That's a good way to think about it. Now, you might be wondering how we actually find this magical CM, especially for complicated objects. Well, Feynman gives us a neat trick. Break it down.
Okay, let's unpack that.
Imagine you have a weirdly shaped object. You can divide it into smaller, simpler parts like squares or triangles. Find the CM of each part, and then you can basically average those points to find the CM of the entire thing. It's like solving a puzzle from the inside out.
So if one part of the object is heavier, its CM matters more in that average, right?
You got it. It's like the heavier part gets more votes in deciding the overall CM. But here's where it gets really interesting. This CM concept isn't just some theoretical physics thing. It's the key to understanding how objects move in the real world.
You mean it's connected to those laws of motion that Newton figured out?
Absolutely. One of the most amazing things about Newton's laws is that they apply to everything, from a dropped pen to the planets in our solar system.
So the same rules that govern that pen falling to the Earth also explain how planets orbit the sun.
Exactly. By focusing on the CM and the total external force acting on an object, we can predict how that object will move. Whether it's a basketball flying through the air or a galaxy swirling through space, the CM helps us make sense of those movements.
That's incredible. It's like having a secret code to unlock the universe's movements. That's mind-blowing. Okay, so we've got this CM that helps us understand how things move in a straight line. But what about when things start spinning? That seems way more complicated.
You're right, spinning objects add a whole new layer of complexity. That's where moment of inertia comes in. It's like the rotational twin of mass.
Okay, break that down for me.
Think of it this way. A heavier object takes more force to get moving in a straight line, right? Well, an object with a larger moment of inertia is harder to get rotating. It's like it has more resistance to spinning.
So something like a bowling ball would have a higher moment of inertia than, say, a tennis ball.
You got it. And the farther the mass is from the axis of rotation, the harder it is to spin. Feynman uses the example of a rod to illustrate this.
Okay, I'm picturing a rod.
It's much easier to spin the rod around its center than to swing it like a baseball bat from one end. That's because spinning it around the center gives it a lower moment of inertia.
That makes sense. So how do we figure out this moment of inertia for different objects? Is there some complex equation?
There is, but thankfully Feynman gives us a handy tool called the parallel axis theorem. It lets us calculate the moment of inertia around any axis, as long as we know the moment of inertia around a parallel axis that goes through the object's CM. It's like having a shortcut.
So we can use the CM as a reference point to make these calculations easier. Clever. But all this spinning must involve some kind of energy, right?
Absolutely. That energy is called rotational kinetic energy. It depends on both the moment of inertia and how fast the object is spinning, what we call its angular velocity. And here's where things get really wild. This energy can change, even if it seems like it shouldn't.
Wait, what do you mean? Give me an example.
Imagine you're at the park, spinning on one of those playground merry-go-rounds with your arms outstretched. Now picture suddenly pulling your arms in close to your body. What happens?
Well, I know from experience that I'll start spinning faster.
Exactly. You've decreased your moment of inertia by bringing your mass closer to your axis of rotation. But here's the thing, your rotational kinetic energy actually increases.
Hold on, that seems counterintuitive. Where does that extra energy come from? It's not like it magically appears out of thin air.
You're right, the extra energy comes from the work you do when you pull your arms in. You're working against something called centrifugal force.
Ah, that outward force you feel when you're spinning, like you're being flung away from the center.
Exactly. When you pull your arms in, you're overcoming that centrifugal force. And that effort is what provides the extra energy to make you spin faster. It's all connected.
That's so cool. So this moment of inertia isn't just some abstract physics concept. It's directly affecting how our bodies move and how much energy we need to use when we spin.
Okay, this is blowing my mind a little bit. It's pretty amazing, right? And this concept of rotating frames of reference leads us to another fascinating phenomenon that Feynman discusses, the Coriolis force.
Oh, I've heard of this. It's the reason why hurricanes spin, right?
You got it. It's this bizarre force that pops up when we're dealing with objects that are moving within a rotating system.
Okay, I'm intrigued.
Yeah.
Tell me more about this Coriolis force. Okay, so we're about to unravel the mystery of the Coriolis force on that spinning turntable. I'm ready. Hit me with your physics wisdom.
All right, let's break it down. Remember angular momentum. That measure of how much an object resists changes to its rotation.
Right.
It has to be conserved, like a fundamental rule of the universe.
Right, like that figure skater pulling their arms in to spin faster. Their angular momentum stays the same even though they speed up.
Exactly. Now let's go back to you spinning on that turntable. As you pull your arms in, your torso, the central part of your body, actually spins faster, even though you haven't applied any new twisting force to it directly.
That's wild. So where is that extra spin coming from? It's like some invisible force is giving my torso a boost.
That invisible force is our friend the Coriolis force. It's not just a sideways push, it can also speed up or slow down rotation. To really grasp this, let's put on our imagination hats and envision two different viewpoints.
Okay.
I'm picturing two people. One standing on solid ground watching the turntable spin, let's call her Sarah, and the other one is, well, me, spinning on the turntable.
Perfect. Now imagine you're holding an object, say a tennis ball, and you try to slide it outwards across the turntable while it's spinning. From Sarah's perspective, standing still on the ground, the ball isn't moving in a straight line at all.
It would look like the ball is curving, right?
Yeah.
Because the turntable is turning underneath it.
Exactly. But from your perspective on the spinning turntable, it feels like some force is pushing the ball sideways, making it curve. That's the Coriolis force messing with your perception.
So it's like the Coriolis force is this weird side effect of trying to move in a straight line while you're stuck in a rotating environment. You got it. And it all boils down to this. To make something curve, there needs to be a real force acting on it. In this case, you're unconsciously applying that force to the ball as you try to slide it outward, counteracting the Coriolis force.
Wow, so even though it feels like this mysterious force is acting on the ball, it's really just an illusion caused by our rotating perspective.
Precisely. And that's the beauty of physics. Uncovering these hidden connections and understanding how our perception of the world can be skewed by our frame of reference.
This deep dive has been incredible. We've explored how something as seemingly simple as a spinning turntable can reveal these mind-bending physics principles like center of mass, moment of inertia, and the Coriolis force. It makes you appreciate the elegance and complexity of the universe in a whole new way.
Absolutely. It just goes to show there's always more to discover, even in the most everyday experiences.
So the next time you're spinning on a playground roundabout or watching a basketball soar through the air, take a moment to consider the invisible forces and principles at play. Thanks for joining us on the Deep Dive.